in previous class I was teaching you about rectifier, about half wave rectifier and center tap rectifier. Okay, so in this class I will teach you about bridge rectifier. So first of all we will see the circuit diagram of a bridge rectifier. Say this is diode D1, D2, D3 and this is D4. This is the circuit diagram of a full wave bridge rectifier. Okay, this is AC input. Okay, say this is VI. VI it is equal to, how we can write VI? VI it is equal to Vm sin omega t. Okay, or we can write Vm sin theta like this. Okay, so this is primary of the transformer and this is secondary of the transformer. It has a turns ratio of N1 and it has turns ratio of N2. Okay, and this input voltage is the voltage that is applied to the primary of the transformer, and Vi is the voltage that is across the secondary of this transformer. So Vi it is equal to Vm sin omega t or Vm sin theta. Okay, so this circuit will work like this. So we will see its working. How this circuit works. Okay, so first of all we will draw the input waveform. Suppose this is Vi versus theta and peak amplitude is say Vm and in the negative side it is minus Vm. This is Vm plus Vm and minus Vm. Okay, this is Vi versus theta, so it is 0, pi, 2 pi, 3 pi like this. So we have to see the output voltage V out across V out, this is V out across this RL. RL is the load resistor. So in full wave bridge rectifier circuit we are using 4 diodes D1, D2, D3 and D4. These are the 4 diodes that are used and one load resistor is used. load resistor is represented by RL. Okay, and this is secondary side of the transformer and this is primary side of the transformer. Okay, now during forward bias, what will happen? See, during this from 0 to pi, this signal, this is positive and this is negative. Okay, so during positive half, right, first during positive half of input. Okay, during positive half of this input, what will happen across this circuit? Okay, so during this, during 0 to pi, this input signal is positive, so it will be Vi, it is equal to Vm sin theta. So it is plus and here it is minus. Peak value is Vm. This is the peak value Vm. Vi, it is equal to, how we can write Vi? Vi, it is equal to Vm sin theta. So peak value is Vm. Now during positive half of the input, polarity across the secondary of the transformer, it here at this place it is plus and this place it is minus. Okay, so for this, now this is positive, so what will be the direction of current? Current flows from higher potential to lower potential, so we have to see the direction of current. So here if it is positive and if it is negative potential, so this positive it is connected to, this is P side and this is N side. So this is forward bias, D2 is forward bias, we can write D2, it is in forward bias condition. Similarly D3, it is in forward bias condition, whereas D1 and D4 and D4, these are in reverse bias condition. You can see during positive half of this input signal, polarity across the secondary of the transformer, it is plus and here it is minus. Because of this, only D2 and D3, these are in forward bias, whereas these two diodes are in reverse bias. Due to this, what will happen? See, if we are considering diode as ideal diode, then in that case, if it is in forward bias, so we have to sort it. This is replaced with a sort. This diode, it is replaced with a sort. Now again D3, we have to replace it with sort. Okay, now D2 and D4, sorry, D1 and D4, these two diodes are in reverse bias condition, so it is open. Okay, so this is the condition when Vin is from 0 to pi during positive half of the input signal. Diode D2 and D3, these are diode D2 is on, diode D3 is on, and this is D4 off, D1 it is off. Okay, so the direction of current, it will move from higher potential, that is positive potential. Direction of current will be like this. this is the direction of current from higher potential, that is positive. It is going like this from D2 through resistor like this. Okay. So what will be the polarity of V0 across RL? It is here it is plus and here it is minus. This is in positive half cycle. Okay. So output will be equal to input, this input. Again here it is Vm. So this is from 0 to pi. Now for negative half cycle, means from pi to 2 pi, we have to see for negative half cycle. Now see for negative half cycle, that is when Vi is from pi to 2 pi. Okay. So this is the circuit diagram of full wave bridge rectifier. Okay. So this is diode D1, this is say D2, this is say D3, and this is say D4. Okay. This is D1, D2, D3, and this is say D4. Okay. Now from pi to 2 pi, this is negative. For this negative half cycle, for negative half cycle of input, what will happen? Diode D2 and diode D4, this will be in on condition. Okay, that is on condition means forward bias condition. Similarly, diode D1 and D3, this will be in off condition, and these are in reverse bias. Okay, so we can remove D1 and D3, and D2 and D4 will be sorted. We have to remove this and we have to make sort, and this is open. Okay. Now the polarity is changed. Here it is negative and here it is positive in the negative half cycle. Okay. This is negative and this is positive. Okay. So it is plus. So direction of current, it will be always from higher potential to lower potential. Okay. So D2 and D4 both are in forward bias condition. So direction of current, it will be like this. This is the direction of current from higher potential to lower potential. Okay. Again, the polarity of V0, it is like this. For positive half, polarity is again V0, and for this also it is V0, and the polarity is same. So for negative half cycle, it will be the same, output will be same, and polarity is both are same. So we can draw the waveform like this, output waveform, it is like this. Similarly for this input, it will be like this. Okay. Here it is Vm, this is also Vm. Okay. So in this way we can draw the output waveform. So this is the working principle of full wave bridge rectifier circuit. Okay. So a full wave bridge rectifier circuit gets output in both positive half as well as negative half of the input. So here IDC or VDC, it increases as compared to half wave rectifier. So we will see in case of bridge rectifier, that is full wave bridge rectifier, I RMS it is equal to Im by root 2, V RMS it is equal to Vm by root 2, and IDC it is equal to 2Im by pi, and VDC equal to 2Vm by pi. In half wave rectifier, we have seen that IDC and VDC. IDC it is equal to Im by pi in half wave rectifier. But here, in the output from 0 to pi and 2 pi. In half wave rectifier, during positive half, during only one half of the input, output we are getting the output. But in case of full wave rectifier, for both positive as well as for negative half cycle, we are getting the output. So IDC it is 2 times as that of the IDC of half wave rectifier. Okay. So based on this, we can calculate first output frequency F out, that is output frequency of the signal. So again we can see this is the graph between V out versus theta, and this is the graph between V in versus theta. Say 0, pi and 2 pi. Here it is 0, pi, 2 pi. Okay. Now here we can see like this. Again for 3 pi it is like this, and for 4 pi it is like this. 2 pi, here it is 3 pi, and here it is 4 pi. Okay. Now you can see the time period of the input signal is say T1, and time period of the output signal is T2, because from 0 to pi it is this signal, the same signal it is repeating. So time period is T2, and here time period is T1, and T1 it is equal to 2 times T2. So we can say that output frequency it is equal to 2 times of the input frequency, because here time period is 2 times as compared to this time period. So output frequency is inversely proportional to time period. So this output frequency of this signal, it is 2 times the input frequency of this signal. Okay. So suppose the frequency is say Fi, and here it is the frequency of this signal is F out. So F out it is equal to 2 times as that of Fi. Okay. Now we will see about ripple factor. Second is ripple factor. How to calculate the ripple factor in this type of rectifier, full wave bridge rectifier circuit. Okay. So what is ripple factor? Ripple factor, say this is the input signal, and for this corresponding input signal, say this is Vi versus theta. This is V output versus theta. Okay. Now, this is the rectifier output, full wave bridge rectifier output versus theta, and this is the Vm, and here it is Vm, and here it is minus Vm. Now, in the rectified output, it contains both AC as well as DC component. Means this is pulsating DC. Output of full wave bridge rectifier is pulsating DC. Pulsating DC. So why it is known as pulsating DC? Output of a rectifier, it is pulsating DC in nature, because it is not pure DC, but some ripples are present in the output. Because of this, it is known as pulsating DC. This is the output of rectifier. It is pulsating DC. In the output, both AC component and DC component both are present. Okay. So lesser the AC component in the output, better will be the rectifier circuit. Okay. So how we can calculate the ripple factor? Ripple factor, it is equal to RMS value. Say for current, it is I RMS value of AC component divided by DC component of the rectifier output. Suppose this is the rectifier output. So it contains AC as well as DC. Okay. So how we can define ripple factor of full wave bridge rectifier circuit? Okay. Ripple factor, it is the ratio of RMS value of AC component divided by DC component of the rectified output. Okay. So this is equal to IRMS AC component divided by IDC. Okay. So it can be written like this: I RMS load current, okay, square minus IDC square divided by IDC. What is this IRMS? IRMS is the IRMS, it is the load current, RMS value of load current, that is the current which is flowing across the load RL. Okay. So it is equal to IRMS divided by IDC square minus 1. Okay. So we can find the ripple factor under root of IRMS divided by IDC square minus 1. So it is equal to, what is IRMS in case of full wave bridge rectifier circuit? It is equal to Im by root 2 divided by IDC, it is 2Im by pi square minus 1. So it is equal to, finally it is equal to 0.482. Okay. In case of half wave rectifier, it was coming as 1.21. This was in case of half wave rectifier. In case of full wave bridge rectifier, ripple factor it is coming as 0.482. So which type of rectifier is better? Full wave bridge rectifier, it will be better because its ripple factor, this is ripple factor, it is lesser. Okay, so for an ideal rectifier circuit, generally ripple factor in ideal case it will be equal to 0. Okay, but practically it is very possible to get ripple factor it is equal to 0. Okay, so for a full wave bridge rectifier circuit, its ripple factor is 0.482. So here the AC component it is lesser in the rectifier output as compared to half wave rectifier. Okay, then we will calculate efficiency. We will calculate rectifier efficiency. So rectifier efficiency can be calculated like this. It is equal to output power across the load, output load divided by P in. Rectifier efficiency it is equal to P out divided by P in. Okay, so P out is the output power across the load resistor RL, and P in, that is the input power after the secondary of the transformer. Okay, then it is equal to IDC square into RL divided by, it is IRMS square into RF plus RL. So it is equal to IDC by RMS square into 1 divided by 1 plus RF by RL. What is this RF? RF is the forward resistance of the diode and RL is the load resistor. So this ratio IDC by IRMS, IDC can be expressed as 2Im by pi square divided by IRMS. IRMS it is equal to Im by root 2 square into 1 divided by 1 plus RF by RL. So its maximum value eta max it is equal to 0.812. Eta max it is equal to 0.812. So in terms of percentage, it is equal to 81.2%. Okay, so the efficiency of a full wave bridge rectifier it is equal to 81.2%. Okay, so it is double as compared to half wave rectifier. Then we will study about peak inverse voltage of this rectifier. Peak inverse voltage of full wave bridge rectifier. So the circuit diagram, you can see the circuit diagram of a full wave bridge rectifier. It is like this. Say this is V naught. Okay, and this is AC input. Okay. Now this is the circuit diagram of a full wave bridge rectifier circuit. Okay. So we can apply for positive half and for negative half. Okay. So suppose for negative half of this, this will be off, and again this will be off. Only this transistor, it will be this diode, it will be in on condition, and this will be in on condition. Okay. So here it is peak inverse voltage. So peak inverse voltage is the maximum reverse voltage that a diode can withstand. So it is equal to Vm. Here it is Vm. Okay. So peak inverse voltage in case of full wave bridge rectifier circuit, it is equal to Vm. What is Vm? Vm is, here it is Vm. Vi, it is equal to Vm sin theta, where Vm is the peak amplitude. Here it is Vi is equal to Vm sin theta. So it is the Vm is the peak amplitude of the AC signal that appears across the secondary of the transformer. Okay. So peak inverse voltage in case of full wave bridge rectifier circuit, it is equal to Vm. It is equal to Vm. Okay. So we have studied three types of rectifier circuit. So we have studied three types of rectifier circuit. So we can compare them. First is half wave rectifier. Second one is full wave. In full wave we have studied center tap full wave rectifier, and third one is bridge rectifier. So these two are full wave rectifier. These two are full wave rectifier, and this is half wave rectifier. So we can compare based number of diodes. We can compare based on the number of diodes. So here number of diode, it will be only one. In center tap it is 2. In bridge rectifier it is 4. Then we can write transformer necessary. In case of half wave rectifier, transformer is not necessary. Okay. And again here for bridge rectifier, this is, you can write bridge rectifier, and here it is center tap full wave rectifier. In case of center tap full wave rectifier, transformer is very essential. Okay. And it is center tap full wave rectifier. Center tap transformer is required. Then we can write IRMS. So here IRMS, it is equal to Im by 2. Here it is IRMS, it is equal to Im by root 2. For this bridge rectifier, it is again Im by root 2. Okay, Im by 2, Im by root 2, again Im by root 2. Then we will see IDC. Here it is Im by pi, and here DC component, here it will be 2 times as compared to half wave. So it is 2Im by pi, and here it is again 2Im by pi. Then we will see peak inverse voltage. Peak inverse voltage in case of half wave rectifier, it is Vm. In case of center tap full wave rectifier, it is 2 Vm. In case of bridge rectifier, it is again Vm. Vm is the peak amplitude across the secondary of the transformer. Okay. Then we can write ripple factor 1.21, and for center tap full wave rectifier it is 0.482. Again here it is 0.482. Then we will see the maximum efficiency, rectifier efficiency. That is maximum rectifier efficiency. What it will be? In case of half wave rectifier, it is 40.6%. It is 40.6%. This is the maximum rectifier efficiency. Again, it is 2 times. So it is 81.2%. Here again it is 2 times as compared to half wave rectifier. Then we will see F out. F out, here it is equal to F in. Here it is equal to 2Fi. Again here it is 2Fi. So we can see in case of half wave rectifier, the number of diodes used, it is 1, whereas in case of center tap full wave rectifier, there is 2 number of diodes are used. In case of bridge rectifier, 4 number of PN junction diodes are used, okay, or crystal diodes are used. Then in case of rectifier, only transformer is very essential in case of center tap full wave rectifier. In half wave rectifier and in bridge rectifier, transformer is generally, it may be required or it may not be required, okay. But here in case of center tap full wave rectifier, it is very essential. IRMS, you can see here it is Im by root 2, it is Im by root 2, Im by root 2, and here it is Im by 2 for a half wave rectifier. Similarly, IDC, it is IDC of full wave rectifier, it is 2 times as compared to the IDC of half wave rectifier. Peak inverse voltage, we are saying that it is 2 Vm in case of center tap full wave rectifier circuit. Okay. So what is peak inverse voltage? It is the maximum reverse voltage that a diode can withstand. Then ripple factor. Ripple factor in case of half wave rectifier, it is 1.21, and it is very much high as compared to full wave rectifier. So we can see that in case of half wave rectifier circuit, in the output of the rectifier, AC components are more as compared to full wave rectifier circuit. Okay. So here we can see that the ripple factor, it is more as compared to full wave rectifier circuit. because in the output AC components are more here, whereas AC components are less in case of full wave rectifier. That is why ripple factor it is more. Then rectifier efficiency. Rectifier efficiency, again the same logic here. DC output, DC component is more in case of full wave rectifier as compared to half wave rectifier. So rectifier efficiency, it is maximum rectifier efficiency, it is 40.6% in case of half wave rectifier, whereas in case of full wave rectifier it is 81.2 in both the cases. Now the output frequency across the load, here it is for half wave rectifier, the output frequency of the signal and the input frequency of the signal both are same, but in case of center tapped full wave rectifier and in case of bridge rectifier circuit, output frequency it is 2 times as compared to the input frequency. Okay, so this is the summary of rectifier circuit. Okay, thank you.